Today we're going to take a look at Chapter 6, Section 2. We're going to look at similar polygons. So as the subtitle would suggest, this is similar to congruence, but not exactly the same. So let's get started. What does it mean to be similar? Well, in a word, proportional. All right. And in our last video, we talked about proportions. Proportions are the main reason for what it means to be similar. And last year in 7th grade, that's really what they showed you. There is one other piece that we want to include. So take a look. We can say that polygons are similar, in other words, they're proportional, if and only if corresponding angles are congruent. So that should look familiar. That's very similar to what we did with congruent triangles, congruent polygons, whatever. So corresponding angles have to be congruent. So that's one aspect. The other aspect is, of course, that corresponding sides are proportional. So 1, 2. Both ideas have to be met. The symbol that we use to represent similar is a tilde. If we have one of those under an equal sign, remember that means congruent. With the tilde all on its own, it's read as similar to. So take a look. I got two figures here. I know that they're similar. First, all the corresponding angles are indeed congruent, so we can check that box. I also can see that all of the sides are proportional. Take a look. If I compare 10 to 5, and then I compare, say, 8 to 4, both of these have a relationship of 2 to 1. And notice that continues on with 6 to 3, 2 to 1, and then 5 to 2.5, still a 2 to 1 relationship. So the sides are proportional, the angles that all match are congruent, so these two figures are similar. Now, congruent figures are also similar. Their relationship, however, is just a 1-to-1 relationship. So for example, your hands, not only are they similar, they're also congruent. So again, congruent, yes. Similar, yes, but not a very interesting similar situation. So if you do have two figures the exact same size, technically, yes, they're similar. They're just not very interesting. Let's take a look at similarity statements. They are all but identical to what we do with congruence. The only addition is, of course, the symbol. So notice in this particular case, we had A and E matched up. So notice A and E just happened to be first. B and F happened to be second because they match. C and G match up, so they're next. And then, of course, D with H, they match. Congruent angle lists, the same as what we do with congruent polygons. So again, all of those list out. This is the only difference here between congruence and similarity. With congruence, again, we make a similar list to what you see here, comparing all the sides. Here, we're going to take all the sides and make a proportion, kind of like what we did here. Notice I compared AD over EH, or I compared DC and HG, and so on. We compare all of those together to make the same proportion. So in this case, our proportion, if we compared, say, large to small, for example, our 10 over 5, is, of course, 2 over 1, and all of those have that same relationship. So we can write that proportion out this way, not just two ratios comparing, but all 4 or 5 or how many sets of sides you've got. So what causes that proportionality? All right. Well, the proportionality that we get is due to what we call a scale factor. Right? This is the number that allows us to either multiply or divide, as the case could be, in order to make these two side lengths work out. So take a look. If I'm comparing DC and HG, we get a 12 to 6 relationship. If we go the other direction, which we can, we would get a 6 over 12 relation. So in this top one, large to small, our scale factor is 2 over 1 or just 2, showing that this is twice the size to that. If we go small to large, we would get 6 over 12 or 1 over 2, or you could say 0.5 if you'd like, showing that this figure is 1/2 the size than what we have here in terms of side lengths. So if you're asked for scale factor, there are two potentials out there depending on how you create that comparison. If you go from, say, large to small, then it could look like this. Or if you're going from, say, small to large, then it would look like this. Notice our scale factors, regardless of direction, end up as reciprocals of each other. So if you're happening to asked a question on this, say on a Google form or a test or something, and you thought it was 2, but the correct answer is 1/2, well, that means you did it in the wrong direction. So again, if I'm comparing large to small, well, then that's probably what it's going to look like. If I compare small to large, then it's going to look something like this. All right? Let's look at some examples here. Let's figure out if we've got similar figures or if they just look a lot alike. So our similar figures here, I notice I've got 60 and 60 that means this third angle is also 60, so that's good to know. And since it's equal angular, that means it's also equilateral. So we'll go ahead and write those in. For our smaller triangle, we can play a similar game. If we've got two 60s here, then that means this is also 60. And again, if it's equal angular, that means it's equilateral. So let's look. All the angles match. Cool. So angles are congruent. And all of the sides create this 3-to-7 relationship. In other words, they're proportional. Which means, ta-da, we have similar figures. Right? Let's look at this one. I noticed that all of the angles seem to match up. So we've got angles congruent. So we can check that off. Let's look at sides. I've got a 4-to-6 and another 4-to-6. So that seems to match up. So 4-to-6, or in other words, a 2-to-3 relationship if we wanted to simplify it. Let's see if we get the same relationship here. So if I compare 3 to 9 and a half, or 9 halves rather, so we could rewrite that if we wanted as 3 over 4.5. Again, half of 9 there, 4.5. We can divide that out real quick. So 3 divided by 4.5. And sure enough, we get that 0.6 repeating, which we know is another way of talking about 2/3. So cool. We have things that are proportional, or sides, that is. So we're proportional, angles are congruent. Excellent. We have similar figures. Forgot one, are there? Okay. Now, obviously, if we didn't get our scale factors working out the same, or if we did have angles that were mismatched, then obviously we would have a situation that's not similar, and we'd be okay with that too. We don't really care one way or the other, just so long as we know. Let's try some others. This time we're told up front that they are similar figures. What we're going to try to do is find x. We're also going to write a similarity statement, and it looks like we need to find some missing sides and write a scale factor. Holy cow, we got a lot to do. Let's start with the similarity statements. Those are pretty easy to write. So we've got triangle A, B, C. So there it is, A, B, C. I know that it is similar. If I could write a tilde, there we go. It is similar to triangle. A matches with D, B matches with E, and then C, of course, would have to match with F. So there we go, similarity statement, check. Find X. Well, let's set up our proportion. I know 21 matches up with X, and that 27, notice these match up, go with 18. Right? Now I notice in this case, if I try to do cross products, that multiplying 27 by x just gives me 27x, and then I have to divide it anyway, so I'm not going to do that. So what I'm going to do is take 21 multiplied by 18 and divide by 27, and just save myself the heartache. Otherwise, I'd have to multiply over here and then divide, and that's silly. So we'll take 21 multiplied by 18 divided by 27, and that gives us a distance of 14 for x. So we found x. We also found the measure of the indicated side, so excuse me, for df, so that's 14. Now we need a scale factor. I'm going to go from large to small, so that is 21 over 14. I can divide both of those by 7, so that gives me 3 over 2 as a scale factor. Again, if you did it the other way around, if you had 2 over 3, that would be acceptable. Notice it doesn't tell us a set direction in this case, so either one would work. Let's try 7. Let's get our similarity statement first. So I know that we've got quadrilateral A, B, C, D. There it is. And it is going to be similar. A matches with E. B matches with F. C matches with G. D matches with H. So that looks good. Let's go ahead and work this out. So let's see here. We've got to find x, so there they are. So let's see, 10 matches up. So 10 here matches up with x, subtract 3 there. 14 matches up with x added to 5 there. So let's work. So we're going to multiply 10 by x plus 5, so that's 10x x plus 50. 14 times x subtract 3, so that would be 14x subtract, what is that, 30, 42? 42, looks good. Let's subtract 10x on both sides. That's 4x subtract 42 equals 50. All right. Let's add 42 rather to both sides because that is subtraction. So add 42 to both sides. That would give me 92. And then all we got to do is take 92 and divide it by 4. That gives me 23 for x. Awesome. So we found x. In this case, though, we're going to have to take x and plug it in to find our missing side. So let's see here. We needed FE, so we need this one. HE, or EH rather, so this one. And then FG or GF, so this one here. All right, well, let's write them in. 23 for x. So if I take 23 and subtract 3, that is 20 for this side. 23 added to 5 is 28. And then we need to figure out this one. Well, notice these sides, let's go ahead and do our scale factor. If we go large to small, that's 20 to 10, or simply 2. 28 to 14 is still 2. So what number could we have here that we would multiply 16 by 2 to get to that number? Well, 16 times 2 is, of course, 32. And that is our missing side. So yeah, we don't have to work out any real fancy proportion there. We can just simply use what we know about our ratios to find that number pretty quick. Simple enough. Notice it's just proportions, guys. That's all we're doing today. Simply working through proportions and adding a little bit of these similarity statements. Not a deal. All right, let's try 2 more, and then we'll be good. Same deal. We need a similarity statement. Find x, measures of our indicated sides, and then, of course, the scale factor. I always like starting with the similarity statement. They're just easier to put together that way. So A, B, C, D is similar. A matches with E, what do you know? B with F, C with G, D with H. That seems familiar. Or similar. Anyway, on we go. We need to find x, so let's do that. So it looks like CD matches up with GH, so that's x subtract 1 and then 5. Those are like items. And then we've got x added to 1, and that matches up with 8. All right, well, let's do our cross products and see where we end up. I'll get 8x subtract 8 when we multiply, and then 5x added to 5. Looks good. We'll subtract 5x on both sides. So that gives me 3x. I'll go ahead and add 8 to both sides. So that's 3x is equal to, what is that, 13. If we divide that out, we get, what is that, 4 1/3? If you'd rather write it as a decimal, 4.3 repeating. I like 4 1/3 personally. So now we know x, we need to find our missing side. So in this case, AB it looks like, and CD. All right, well, AB is simple enough. We'll just add 1 to this. So 5 1/3. And then for the other side, we're subtracting 1. So that's just simply 3 1/3. And then we need a scale factor. Again, I'm going to go large to small. So in this case, 5 to 3 1/3. So let's do that. 5 divided by 3 1/3. Looks like 1 1/2. Or we could say 3 to 2. I think I'm going to go with the 3 to 2. That looks like a better scale factor. Obviously, both are the same, but 3 over 2 or 1.5, it'll work. Let's do the last one. Oh, goodness. They've only labeled 2 of our angles here, so let's see what we can work out. Angle ECD and angle ACB are the same. Those are vertical. And then by the third angle theorem for our triangles here, angle E and angle A. Excellent. So let's grit that similarity statement. So triangle ABC is similar to triangle. Let me see here. A matches with E, we said. B matches with D. And then, of course, C with C. That was simple enough. So 4 matches up with 6 on the other side. And then X added to 7 matches up with 12 subtract X. All right, let's start our cross multiplication. 4 times 12 is 48. 4 times negative x is a negative 4x, or we can write it as subtract 4x, your call. 6 times x is 6x, and 6 times 7 is 42. I'm going to add the 4x to start just so I can keep things positive. So that's a 10x added to 42. We'll keep the 48 over here. Subtract 42 on both sides, so that is 6 is equal to 10x. And then when we divide that out, we can get 0.6 if you're a decimal person, or if you don't like the decimal, that's 3/5 as a fraction. Either of those answers for x would work. All right, we need to find AC, so this side here, and CE, this side here. Well, if I add 7 to 0.6, that's just 7.6, or 7 3/5. If I subtract 0.6, say from 12, that is 11.4, or 11 2/5, your call. Our scale factor, again, large to small, I'm going to write it as 6 to 4, which is simply 3 to 2. Funny, they have the exact same scale factor. So that's what we're doing today. We're simply making these comparisons, looking if we have similar items or not. If we do, wonderful. If we don't, that's cool too, just so long as we know why. If you have any questions, make sure you bring them with you to class. Otherwise, have a good day, folks.